This is Dr. Rebecca Harbison. She grew up in Lincoln, and as she grew up here, she went to UNL. She got her bachelor's in physics and math in 2005 from UNL, so she knows some people. She went on to Cornell and got her PhD in astronomy just this past September, I think, so fresh PhD graduate, and she's going to give a talk on Saturn's rings and the particle size in them. And then afterwards, we'll do some questions, and then we'll have a Q&A session for undergraduates to talk about grad school.
All right, thank you for the introduction. So, as was said, I'm going to give a talk on the smallest free ring particles within Saturn's rings. First, I'd like to acknowledge a few people. This is work I've published in the journal Icarus as of 2013. So I'd like to acknowledge my co-authors, Philip Nicholson of Cornell and Matthew Hedman, now of the University of Idaho. And I'd also like to acknowledge my Cornell dissertation committee, Joseph Burns, Rachel Bean, and Richard Lovelace. So I thought I'd start with a little bit with a step back, which is thought I'd start with the outline and then go into the motivation. So first I'd give an introduction to Saturn's rings and to the Cassini spacecraft, which is currently in orbit around Saturn. Also talk about the method I used to get at the sizes of ring particles, which is occultations, which I'll go into in a little more detail. And also talk about how we parameter the size of a collection of objects, such as the bodies that make up Saturn's rings, in a particle size distribution. So then I'm going to go into the data and data analysis of the particular observations I've used, the solar occultations of the sun. And then I'll go present my results first of the C ring, and then of the A ring. And then I'll go into my conclusions. But first, I thought I'd take a step back and go into the motivation. Why do we care what sizes Saturnian ring particles are? So the first from the kind of most specific to most general is that the rings, while they look very simple in like a small telescope, as we get closer, as one might with Cassini, which you can see in this lovely picture of the outer A ring, you can see more and more complicated things going on. Most models, computational models of ring particles, when they even include the effects of individual ring particles, only really work with the larger stuff. So understanding how good or how bad of an assumption that is, and testing whether or not adding smaller ring particles makes a difference is important for our understanding of ring dynamics, especially in very complicated regions of the rings. The second reason is one of the big, always outstanding and interesting questions about Saturn's rings is how were they formed, where did they come from, how old they are, and how they've changed from then to now. One of the major ways we know about that is to date the rings, which depends on knowing about the mass of the rings. Therefore, if you don't know how much small stuff and how much large stuff there is, you can underestimate the mass of the rings. You might think the rings are a lot younger than they are, which rules out some models of origin. Similarly, knowing that the rings are very old also rules out other models of the ring origin. The third, and as the non-planetary scientist reason, is that why we care about a specific set of rings around a specific planet when there are thousands of planets in the universe, is that the rings are one of the closest examples of what astronomers call a debris disk, a collection of bodies, solid bodies, orbiting a primary. Now these are very common in the universe. Our Earth formed out of a debris disk. These are around other stars forming planets, or the remains after planets have been formed. Saturn just happens to be a close example. It has some very different properties than a protoplanetary disk, but it still lets us test our general models of how disks work in a place where we can take a nice close-up picture to kind of check we understand what's going on. And in fact, some observations done by Cassini of ring phenomena have provided insight into such things as planet formation. So here's a little primer on the rings of Saturn. The main rings of Saturn are basically divided into 3 parts, creatively named the A ring, the B ring, and the C ring. They are made up of, again, as I said, solid pieces of, in this case, water ice with some trace impurities. The reason the rings exist is basically because they're very close to Saturn. They're close enough that the rings own the gravity of the individual bodies within the rings is not as strong as tides from Saturn. So while the gravity wants to pull everything together to make a moon, the tides are strong enough that anything too large gets torn apart. Thus, you end up with a system that's relatively stable over reasonable lifetimes. And as I mentioned, the rings have different distinct regions that you can see here. That the C ring is relatively faint. You might not be able to see where the little arrow is pointing, that there's actually something there rather than empty space. B ring is relatively bright, and the A ring is in kind of the middle. This actually reflects the density of material within the rings. The C ring is relatively diffuse, at least compared to the other two. The B ring is relatively opaque, and the A ring is kind of in the middle. So the Cassini spacecraft entered orbit around Saturn in 2004, around when I was starting my senior year here at UNL, and making it perfectly timed to do a dissertation project on the data. It is placed into an orbit that involves it frequently flying by Titan. In addition to the interesting science one can do at Titan, which is many other talks, the Titan's gravity, Titan, Saturn's largest moon, its gravity is enough to allow us to change the orbit with sometimes the injudicious use of a little bit of thrusters. This lets us have many different orbits, which lets us do things such as target moons for flybys, or construct an orbit that's well placed for ring observations, or planet observations, or moon observations. And everyone gets a little bit of what they want, but not everything. The reason we have Cassini, our first orbiter around Saturn, is quite simple. Cassini gets much, as I was showing in earlier pictures, Cassini gets much better resolution than even a very large telescope placed on Earth, just because it's so much closer. Pretty self-explanatory. The other thing that's a little less obvious is that Cassini can see geometries that we can't get from Earth. You can see the bottom picture there. It's a very famous one and a very pretty one. And it is a photo of Saturn with the sun behind the planet. We obviously cannot see this from Earth because it would require Saturn going between the Earth and the sun. Yeah, it's something we really would rather not happen. And you can also see that there's a lot going on in this picture, and a lot that other scientists have been working with that we don't see in, for example, the top picture, which has a closer to our view from Earth. And in particular, the work I do, the solar occultation work I do, cannot be done from Earth at all. Because again, it requires the sun, Cassini, being on the opposite side of the planet from the sun, which the Earth does not do. So the instrument I use for my work is the Visible and Infrared Mapping Spectrometer, VIMS. You can see a picture or a diagram of where it is on the spacecraft. The name is thankfully pretty self-explanatory as far as NASA acronyms go. It is a spectrometer. It splits light into a spectrum, allowing us to measure the intensity of light at various wavelengths. It works in the visible and the infrared. In my case, I don't use the visible channels. They are turned off during the observations I'm using. So I have 256 different infrared channels between a little bit blue word of 1 micron to red word of 5.2 microns. So what astronomers consider the near infrared. The other part of its name is it's a mapping spectrometer. This means essentially it takes pictures. So VIMS has a pixel size of 0.5 milliradian by 0.5 milliradian. That number actually becomes important. And it is capable of imaging, though it does so pixel by pixel, rather than exposing all of its pixels at once. That. The other thing, which is not covered in its name, is that VIMS can observe the sun. Now, if you pointed Cassini's primary telescope at the sun, and then overrid all the warnings that tell you that you're not allowed to do this, you would end up with several very broken instruments and many very irate scientists. However, VIMS and a few other instruments have a secondary aperture with a lot of optics whose primary job it is to get rid of sunlight. So they reflect over 99% of the sunlight entering the spacecraft, sending a fraction of 1% into the instrument. This allows you to safely observe the sun. And as to why we might do that,
Excuse me? So what's the ballpark size of this?
I think the figure is Cassini's about the size of a school bus.
Oh, okay.
So I don't have any pictures of, astronauts for scale, but gives you roughly the idea of the size. So what I do is, with this instrument, is I could do an occultation. So an occultation has 3 parts. You have the source, in my case the sun or a star, the receiver, in my case Cassini VIMS, and you point the receiver at the source. That's clear enough. So what you then need is the third part of that triangle, and that's a target. So what's going on here, in this case the rings. So what's going on here is light from the source is shining on the target, and some of it makes it through to the receiver. Because the light has interacted with the target, it tells us something about the target. Alternately, you can do an occultation to learn something about the source. In fact, that's how we learned the size of some of the first learned the size of some stars, was by occultations of using the moon. But in our case, we're looking at the target, not the source. Or fine. So let's zoom in a bit, figure out what happens when you watch the rings get in the way of the sun as seen by Cassini. So here we have a zoom in on what's going on. On the left is the source, or the direction to the source. So in this case, we have sunlight. And on the right is the receiver, helpfully labeled with the eyeball drawing. So, and in the middle we have the ring, which is again made up of bodies of ice. Now, the ring is not completely solid, as I mentioned. It has some bodies and some empty space. So some of the sunlight makes it through the ring and strikes the receiver. Some sunlight is absorbed or reflected by ring particles. Either way, it is not visible by the receiver. This is a useful measurement in and of itself because it provides a nice estimate of how much stuff is between the source and the receiver, in our case the rings, which tells us something about how much material is in between. So we might speak of how much light is absorbed in terms of optical depth, how much light is attenuated when it passes through the rings. However, this is not only a small part of what I've done. So the other thing that can happen, besides absorption and transmission, is diffraction. Just like any type of object, when it encounters a wave, the wave will diffract. So when light encounters a ring particle, it will not only be absorbed by the cross-section of the ring particle, but some of the light will be diffracted. Now, this is a size-dependent property. If you have a small ring particle, things will diffract at a larger angle than a big ring particle. So this is pretty basic physics. And this process goes as roughly order of magnitude the wavelength of light over the size of the body doing the diffraction. So in our case, well, we have an infrared camera. It works from 1 to 5 microns, so let's pick 2. And it has a pixel size of 0.5 milliradian. So if we were to ask, what size of ring particle would we need to diffract sunlight enough to move it from one pixel to the neighboring pixel? We'd get that, well, it's a millimeter-sized ring particle. So if we were to look at the sun, again, with all these optics in the way to make sure we can do so safely, and look for diffraction and look for the effects of diffraction, of sunlight diffracted into neighboring pixels, that would tell us, are there millimeter-sized particles in the ring or not? So what we'd expect to see if there are would be a sort of halo, an aureole around the sun. Now, once we get to the basic question of yes, no, is it there or is it not there, we also want to know, okay, what sizes of ring particles are there? How are they distributed? And how do they compare to the large particles, which from other experiments we know are there? So what we want is not just a yes-no answer to the question, but we want to start to construct a size distribution. How many particles of every size are there? So the model we've chosen is a truncated power law, which, as every astronomer knows, is a good model for everything. So a truncated power law has pretty much 4 parameters. So here is a picture of a truncated power law. It has pretty much 4 parameters. So on this axis, you can see the ring particle size with a log scale. You should see it helpfully labeled millimeter, centimeter, decimeter. And here you can see the log of the number density. So we have, as I said, we have 4 parameters defining this power law. We have the 2 places we're truncating it, the minimum particle size and the maximum particle size, A min and A max. We have the power law index, which measures essentially how much small stuff there is for large stuff. In absolute, if we're writing down the equation, it would be an A to the Q, but here when plotted in log space, it looks it looks exactly like a line. So we can think of it as kind of a slope. We parameterize it as Q, and by convention, Q is positive, so since we know it's a negative power law, we're just putting in a negative sign. The final parameter is the absolute number of particles, essentially a scaling factor. Now this one we're not going to try to fit, and the reason, or at least we're not going to try to fit using the diffraction. What we're going to do is assume that from absorption, we know how much stuff is in the ring. And then we can calculate the number density of particles based on the measure of the optical depth tau, which is measuring the absorption. Now this has to make some assumptions. We have to assume that it's essentially a homogeneous collection of particles randomly distributed in order to properly do the calculation. I have to assume it's not going to clump or aggregate or form aggregates. So we do all that, and that lets us take a measure of, say how much diffraction is going on, and turn it into a statement of, well, what is the size distribution of ring particles? So let's talk a little bit about what was known before I started working. So one thing we know was that this was an interesting problem. We knew that there was lots of ring material that was 1 meter size, 10 meter size, or not 10 meter, 10 centimeter size, and that there was very little ring material that was of bodies smaller than 1 millimeter. However, we weren't definite on the exact lower cutoff size. The only other experiment really trying to pin this down was going on concurrently with Cassini's radio transmitter. On the other hand, we knew the upper limit actually quite well, thanks to Voyager and to other experiments. We knew that if you look at the actual size distribution, not just the model, it steepens markedly at 5 to 10 meters. There's very, very little ring bodies in Saturn's rings, not none, but very little, that are bigger than about 10 meters. So, you know, a couple of rooms, a house maybe. The other is that the differential size distribution had a power law index of about 3, which is actually pretty common in systems like this. The other thing we know is that there's not just one particle size distribution across the entire rings. There's many, or several. So if you consider the values derived for fits for different ring regions. So here I'll walk you through this plot. So on the horizontal axis we have distance from Saturn in 10 to the 6 meters, with the different ring regions that I pointed out earlier set off with dotted lines. And a blue line marking the difference between the inner and outer A ring. As you can see, the vertical axis marks the power law index. Again, this is a differential power law index. Each of the data points represents one previous attempt to measure this power law index. So the red points are from the Voyager radio occultations done when Voyager flew by Saturn. Essentially an occultation was done, but with Voyager as the source, emitting radio waves received by Earth. The blue points are from a stellar occultation. The star passed, or Saturn appeared to pass behind the rings, or Saturn appeared to pass in front of a star, as seen from Earth. You know, a fortuitous accomplishment. While the green data points are the preliminary results from Cassini radio occultations. They haven't been published, but they have been presented and cited in the Saturn from Cassini compilation book. So the general point I want you to take away from this is that the C ring and the outer A ring are similar. They have a power law index that's a bit steeper than 3, while the B ring and the inner to mid A ring are also similar to each other and have a power law index that's slightly shallower than 3. So pretty much the surface area of the ring is dominated by small particles in the C and outer A ring, and dominated by large particles in the B and inner A ring. As I said, we also have some preliminary results for other experiments have some preliminary results of minimum particle size. Here, Voyager was unfortunately not able to give a definite answer, but the other two, the Earth-based stellar occultation and the Cassini radio occultations, were able to give some results. So again, we have distance from Saturn on the horizontal axis with the ring regions marked off with dashed lines. This time we have minimum particle size on the vertical axis. And again, the C ring and the outer A ring are similar. In this case, they have the minimum particle size goes down to somewhere between several millimeters and 1 centimeter. The B ring and the inner A ring are also similar to each other, but different from the C ring and outer A ring. They have a minimum particle size that only goes down to 20 to 30 centimeters. So let's actually start talking about what I did after that very lengthy introduction. Again, the details of this are available in Harbison et al. 2013, published in Icarus. So I have 6 solar occultations, and I'm going to look for light diffracted during these solar occultations by the rings to measure ring particle sizes. So here is an actual image of the sun as taken from Cassini. It is unfortunately not quite as stunning as the things taken by Cassini's camera that I've been showing through most of the introduction. It is reverse contrast, so the light areas are the sky, and the dark areas are where the sun is. You can see the sun takes up several pixels. It's a 12 by 12 image, and we have about 6 series of these images as the sun appears to go behind the rings. Now, if you look at it, and I deliberately reversed the contrast so you would see this. You notice that it does appear like the area around the sun has slightly more signal than, this patch over here or that patch up there. That looks, when you first look at the data, you're like, oh yay, positive result. Only problem, this is an image of the sun outside the rings. There's nothing in the way between the sun and Cassini to be diffracting light. Unfortunately, there is something in the way from Cassini to the VIMS detector that is scattering light. All of those optics that make the sun safe for us to look at also scatter light. And they scatter light in appreciable amounts that weren't noticed till we started flying, and it was too late to do anything about it. So the background in this image is not only kind of patchy and tricky, but it's also about 1/10 of the peak signal we're getting from the sun. And it does scale with the sun. If the sun is behind the rings and the signal drops, the background also drops. So it's essentially measuring the amount of sunlight. But now the problem is the amount of signal we'd expect from any reasonable particle size distribution is about 10 times smaller than this background. So we need a way to essentially deal with some very noisy data that we can, and in a way that does not involve fixing the instruments because it's at Saturn. So we're left with the question of how do we measure, how do we use this data that we collected and measure the smallest ring particles when we have this background? So that requires knowing a little bit of how VIMS should work and how VIMS is actually working. So theoretically, this is what should happen. Light enters the solar port, it's attenuated to safe levels. VIMS creates its images by basically pointing the solar port or the primary telescope in the general direction of the target, and using a small mirror to slightly shift the position of the image onto the imaging surface, such that only a small part of the field of view is collected by the CCD we're using as a receiver. So if you want to build up an image, we essentially first use this mirror to pick out a part of the field, take a pixel, get the entire spectral data, or get the entire spectrum from 0.9 to 5.2 microns. Adjust the mirror to pick up the area beside it, take a spectrum, essentially build up an image pixel by pixel. And then when you get a full image, since we're doing an occultation, things are changing with time, we do it again. So that's what's going on, in theory. In practice, it's a little messier. So in practice, not only is the light entering the spacecraft being attenuated, but it's also being scattered around the spacecraft. So when that mirror picks out the part of the field of view you're imaging, it's also getting some of that scattered light. So if you say we're done with this, exposing this pixel, let's go to this one, the direct signal drops off because this pixel is on the sun, or pointed, is a pixel that's covering part of the sun's image, and this one isn't. However, the scattered signal, the light that's coming in from the sun, bouncing around the spacecraft, and then hitting our detector, that doesn't change because we're not changing the part of the sky we're pointing at. Or rather, it doesn't change as much. You can see that there's still some variation in the background that is due to the instrument and not the sky. So essentially, you have scattered light being a constant signal of measure of how much sunlight we're getting, losing completely all spatial information, while the direct signal measures exactly how much sunlight is hitting this virtual pixel. So that's the key. So what we did is, here are some simulated images explaining what's going on. You notice they look a little nicer than the actual data, because they always do. I've also turned the contrast back to normal. So here is a simulation of what we call an empty cube. A VIMS picture is a cube because, of course, it has 3 dimensions, 2 spatial and 1 spectral. 3 dimensions makes a cube. So here we have an average of what you'd expect to see if you're looking at the sun outside the rings. It's empty. It's an empty cube because there's no ring in the way. So this one would have the instrument scattered light, and it'd have the direct signal, but it'd have no diffraction. Here is what we get when you start add in diffraction. And because these are simulation, you can add in, say, a particle size distribution model that definitely would have diffraction at angles we can see. So let's divide this one by this one. We get something that looks like this. So first of all, you can notice that because you have this background measure of light scattered by the instrument, the transmission, you can see the light absorbed by the ring. Remember, this is all sunlight shining through the ring, entering Cassini. So we still get all the effects of ring. So we still get all the effects of the ring in general. We just lose the spatial information that tells us diffraction is going on. Now, if you look, since this is a nice clean simulation, you can actually see the aureole, the halo you'd expect from diffraction. You can see that the pixels surrounding the spot in the image where the sun is are slightly lighter because have slightly more light in them. However, when you look here, you have to ask yourself, well, where does the light come from? Well, it comes from those pixels that are directly on the sun. You're essentially taking light and moving it out away from the sun. So correspondingly, these pixels have to be dimmer, the ones that are on the sun. They're missing some scattered light. And that comes into our key of how we're going to measure the amount of light scattered by small particles. So we're not going to measure how much light is scattered. We're going to measure how much light is missing. Now, because there are fewer pixels on the source, on the sun, than that are nearby the sun, the signal is stronger, it has a better signal to noise, therefore it makes a cleaner measurement. So that's how we're going to do it. So pretty much once we get the difference, so pretty much what we're going to do is measure the transmission from the background and from the pixels directly on the sun. We're going to say, well, that tells us what the fraction of missing light is, how much light is missing due to being diffracted at angles larger than 1 pixel. And that, if we then have a model of particle sizes, will tell us something about the particle properties. What collection of particles can diffract that much sunlight? So let's talk results. So here we're going to first talk about the C-ring. So even with this idea of let's measure how much light is missing instead of how much light is extra, we still have a very noisy problem. So what we're going to do is, as one does with any sort of noisy problem, is start averaging. So we're going to take for every occultation, we'll take every measurement that occurs within the C-ring and average the result from each individual measurement over one another. We're losing spatial data here, but we're gaining in sensitivity. The other thing we're going to do is start binning in wavelength. VIMS, remember, has 256 infrared channels. So we're going to bin every 8 together. Now, diffraction is spectrally dependent. If you diffract at a larger wavelength, you get a larger angle of diffraction. However, we're trying to pick channels that are relatively close to one another, so the difference between the diffraction at 2.1 microns and 2.12 microns is relatively small. So here we have the result. We have 5 occultations that extended into the C-ring. And from those, we had 3 positive detections, 1 marginal detection, and 1 negative detection. So here we have the positives and the marginal. So on this axis, so each of these panes shows the results from 1 occultation. This axis shows the wavelength in micrometers. We're focusing in on the 2 to a little bit less than 3 because this is where the sensitivity in the instrument is. So this axis shows the amount of missing light in units of transmission. So 0 is no sunlight, and 1 is the amount of sunlight you see when there's nothing in the way, no rings or anything. You can see that this is a fraction of 1%. So if you consider that we had to design the experiment such that we didn't overexpose the sun, we needed to measure things that are a fraction of 1%. Now, each of these points is one of our wavelength VIMS. So each of these points makes up 8 different measures of the amount of missing light averaged together. And the error bars mark the standard deviation in within each bin. You can see that, well, certainly you can see clearly that the top and bottom ones have a positive detection, that there is definitely light missing from the sun, which we are inferring is diffraction. You can see this one is kind of a marginal detection. This point is definitely within 0. This one is also a positive detection. It's a little hard to see that this error bar doesn't quite make it all the way down to 0. So this is the fraction of scattered light. We want to use this to get a measure of particle properties. Now the problem is I talked about the particle size distribution model, and I mentioned it had 3 parameters. That might be a little bit overambitious to try to fit all 3, because what you essentially end up with is a measure of the amount of diffracted light at a very narrow range of wavelengths. So essentially we have 1 measurement per occultation. And since the occultations are covering the same region, they should give the same answer within the various experimental errors. So when you have one measurement and 3 parameters, you have a model that has vastly too many parameters for its number for the data. So for us to ask ourselves, what can we say meaningfully about this model if we can't just give best fit parameters? The first thing that we can say is our experiment is very insensitive to the largest particles. So what we're going to do is just fix the upper size cutoff based on previous results. The second thing was, well, now we have these 2 parameters left: the minimum particle size, our lower cutoff, and the power law index. So what we can say is we can't give you them individually, but we can come up with a function, a kind of a best fit for one parameter given the other, and say which values of these parameters are reasonable given our results. So here we have a plot of the best fit values of the parameters. So here we have power law index on this horizontal axis and minimum particle size on the vertical axis. The line marks the best fit values of those parameters given the fraction of scattered light measured in our 3 positive detections, and the dotted line marks the 1 sigma error bars in the fit. So you can see that robustly we can say that there have to be particles smaller than 2 centimeters or even 1 centimeter within the ring, regardless of what the power law index of the C ring is. The other thing we can say is that if we take a value of the power law index from previous work, say a power law index of 3.1 in the C ring, which I mentioned is a nice mean of previous results for the C ring, we can get a value of the minimum particle size, which is about 4 millimeters rather.
Are these 3 numbers for a Q for those 3 things you had before on the previous slide?
What?
These 3 Q values are for 3 different occultations in your data?
Yes, this curve includes uses the three results from the 3 occultations we did. So this combines all 3 results and gives the best fit value, assuming all 3 results are drawn from the same collection of particles, which seems reasonable since we're sampling the same ring.
And the 3 occultations you had were from the same region of the sea ring?
Yeah, they were covering the entire sea ring. There was some difference in sampling, but we don't think it will make a difference in our results. Sorry, I wasn't clear. So if we compare that to the previous results I mentioned earlier, you can see it actually holds up very well. That the radio science team, which although they use the same spacecraft, they use different instruments, a different team, different methods of analysis, and yet they get the same result, which feels pretty good. And our results are consistent with the previous work done measured by the stellar occultation, which is, they said, around 1 centimeter. And given their error bars and our error bars, they agree with one another. So let's move on to the A ring. So again, we're averaging each of these occultations so we have 6 occultations. We're again averaging spatially. They're taking all the measurements from the beginning, from the innermost point of the A ring to the Encke gap, which is what we kind of consider the boundary between the inner and outer A ring, and spatially averaging all of our data from them. We're also, again, spectrally averaging over 8 wavelength bins. And again, we do that and we get 5 positive detections and 1 negative. So again, you can see here is the horizontal axis plotting wavelength of our 5 different occultations of the same ring region, and vertical axis plotting the fraction of missing light in transmission. And again, you can see that these are while some of them have error bars larger than you might like, these are very clear positive detections. They're clearly not 0. In fact, they look nicer than some of the C-ring stuff. So again, if we want to try to find our best fit values of minimum particle size and power law index, and again, we're going to assume the maximum particle size from previous work because we don't have a very good constraint on it. So again, we have power law index on this axis, minimum particle size on the vertical axis. This line marks the best fit values or the average best fit values for those 5 positive detections I mentioned, or for the fraction of light from those 5 positive detections, with the dotted line marking the 1 sigma error bars. So again, we can say that there is definitely material smaller than 1 centimeter in the inner A ring. If we put in some values of power law index from previous papers into this curve and get out the minimum particle size, we can see that the minimum particle size for a power law index of 2.9 is about 0.6 of a millimeter. Well, if we make the power law index shallower, put it down to 2.75, we actually find only an upper limit that minimum particle size has to be smaller than 1/3 of a millimeter. Now, you might remember from earlier in the talk that this is a bit of a problem, that the stellar occultation results quoted a minimum particle size of 30 centimeters, while the radio science results from Cassini quoted a power law index, or quoted a minimum particle size of 20 centimeters. This work quotes something that's several orders of magnitude smaller. So we're forced to ask ourselves, why did we get different results than these 2 other experiments? And the answer we came up with is that we included something that they did not include, which is something that the behavior the ring does that we call self-gravity waves, and I'm going to explain what those are. So, Self-gravity wakes were seen in computer simulations in the early 2000s. Here is a computer simulation from Salvador. What these simulations do is they take a bunch of meter-sized ring particles in a computer, they put them in orbit around Saturn. They have Saturn's gravity and tides, and they have the ring particles' own gravitational interactions. So you pretty much take this code and you run it. And even if you start the ring particles off randomly distributed, as one does, you end up with structures that organize that look very much like this. These are the same, or a simulation with the same initial conditions, the same number of ring particles, same density, etc., just from two different angles. You can see I marked the direction to Saturn with red arrows. Now, Cassini's pictures are very nice, but they're not good enough to see. They don't have good enough resolution to actually see a self-gravity wake. However, we do see in pictures from Cassini and even from Hubble and in occultations differences in the rings due to viewing angle. That a patch of rings at one angle looks different than the same patch of rings from another. You can kind of see that in this picture, what's going on. Remember, I said those two simulations might be at slightly different points, but they have the same density of ring material, the same stuff.
Are these wakes stable and static?
I'm going to get to that, but I don't think, no. So, but you can see from these pictures that the picture to the left looks a lot less dense than the picture to the right. There's the same amount of material and it's clumped in kind of similar ways, but because of the way you're viewing it, you're not seeing all the gaps. You're not seeing all the gaps between the wakes on the right-hand side. So this is how we know that these things are real, even though we can't actually resolve them yet. So what's going on here is that, remember, the rings are too close to the planet to collect into a moon. That doesn't mean the self-gravity of the rings, it doesn't exist. So the ring particles are trying to clump together, form a moon, while tides are trying to pull them apart. And because this is a very close to the Roche limit, the place where place outside of which you can successfully form a moon out of clumps of material, instead of getting just tides completely winning and randomizing everything, you end up with these structures, these aggregates of ring particles. Now, if I had a movie of one of these simulations, you could see that the presence of a particle within the wake, and even an individual wake in themselves, are not static, as you were asking. That wakes in this region are constantly forming and dissolving, but that part of the A-ring always has them present. Now, why this matters is that because of the A-ring's distance from Saturn and the density of material in the A-ring, it has a self-gravity wake. The C-ring, which I mentioned earlier, and had all those nice results for, is much closer to the planet and has much less dense. So it doesn't do that. It doesn't do this. Now, my models so wakes violate the initial model assumption I made when I was calculating a particle size distribution, which is that finding the number density of ring particles can be found from the optical depth. Basically, to calculate the number density from the optical depth, you have to assume there are no aggregates. Since there are aggregates, you have to take them into account if you want to get the right number density. What happens is these wakes are essentially opaque collections of particles, so they are absorbing light, and often sometimes less efficiently and sometimes more efficiently, depending on the geometry, than just a random assortment of particles. So what happens if you don't include wakes? So wakes mean that fewer particles of all sizes are free to interact with light for a given tau. So a model that includes wakes bind up a fraction of the material into a wake, and it wouldn't diffract like a centimeter-sized ring particle. It would diffract like a 10 to 50 meter self-gravity wake. So a model that includes them would have less diffraction than a model of the same number density of particles, but had them all free floating. Now you remember that there are, even in regions where there are self-gravity wakes like the A-ring, not all particles are within them, so we still see some diffraction. So this means, unfortunately, that in many cases, a model that doesn't include self-gravity wakes, but doesn't include very many small particles, looks exactly the same as a model with self-gravity wakes and small particles. So I'd expect that had previous papers included self-gravity wakes, their minimum particle size would be smaller, which is what I see. And I note that unlike previous experiments, I cannot explain I am very insensitive to large particles, that I cannot explain my results by making a larger particle size cutoff, minimum particle size cutoff, and getting rid of the self-gravity wakes, that I know are there anyways. So I offer this explanation as to why my results are different than previous results, and I would like to move into the conclusions. So I can confirm the minimum particle size of 4 millimeters in the C ring. I state that the minimum particle size of the inner to mid A ring is less than 1 millimeter, which contradicts previous results. But I offer a more general conclusion for other scientists studying the rings of Saturn, in particular the observations of the rings of Saturn, is that when trying to model these results, one must include the effects of the A-ring self-gravity wakes in order to get a more accurate answer. And that explains why my results differ from previous results. Okay, thank you.
If you have questions, raise your hand. I'll take them.
You mentioned at the beginning there was a simultaneous measurement of competitor being taken at the same time. Have you heard anything from their results?
No, but I know the radio science team has historically been very, very slow and careful of their work. I don't really consider them a competitor since they can do different things than I do.
Complementary.
Yes, but complementary work. We also have a team on another project I'm working on that's related, of both using VIMS and the ultraviolet spectrometer to get at some of the larger particles using stellar occultations. That work has not been published yet, and unfortunately I didn't have time to talk about it.
Anybody else?
In your earlier pictures looking through the rings just with a camera, the rings are bright, and I always thought that was due to scattered light, but from what you talked about, it doesn't sound like you should be getting scattered light that's that intense.
That is due to, I am mostly sensitive to diffraction. The rings also are very good at reflecting light, and as they're made of mostly water ice, so they're very bright. So.
But if you're looking at them from behind, they ought to be dark then.
Let me go back to that picture. So the main rings, here I'm going to make a distinction. That's a good quote. The main rings are, well, first off, this is at larger angles than I'm sensitive to. I'm looking at a very, a fraction, essentially a milliradian from the sun, while this is several, up to 10 degrees. And you can see not all the rings are dark. The B ring here are bright. The B ring is dark because of basically the B ring is dense enough that you can't scatter, that essentially trying to see through it is impossible. There's enough stuff in the way. The other distinction here is that this also shows the dusty regions, the dusty diffuse ringlets here and here, which are another can of soup entirely. They have plenty of particles smaller than 1 millimeter.
So can you point out the A, B, and C rings in that?
Yeah, here the A ring is bright, the B ring is dark, the C ring is bright. And these are at large enough angles that you can see basically light reflected off of the ring surface rather than diffraction.
Okay, so it's a different process than what you're looking at?
Yes, yes, exactly.
What waveband is that in?
Let's see, this is a Cassini ISS picture. I don't remember what particular filters were used here. I imagine either, blue or violet, green, and then either red or infrared. I don't remember. Unfortunately, I don't use Cassini's camera, so I only vaguely know which wavelengths they do. I do know it was taken in the visible, though the camera can extend a little bit into the ultraviolet and infrared.
And what's the sorry, just to follow up, what's the dominant source of the fact that you have some illumination on the backside?
Well, the rings, well, first off, it helps that you have no direct sunlight from the planet coming in. So you have essentially either light reflected off of, I guess, crescent ring particles, or light reflected between ring particles.
Could you write down the power law? I'm confused, what is in the power law?
It's pretty, you get to go to the board. So you pretty much have a power law from A min to A max. So the number of ring particles pretty much equal to some constant, let's just call that A naught. So that should be N.
So you are fitting 2 parameters, you said?
3. We're assuming we know this one from the optical depth.
Yeah.
I'm assuming
Yeah, I've
this
seen
one is
that.
technically a free parameter, but I'm not very sensitive to it, so I basically used previous research at other wavelengths.
So then you'd have to put 2.
So I'm only fitting these 2 parameters.
So why do you have different values of Q? I thought if you fit something, you have one value of Q.
Well, what I ended up with was that function, that A min and Q. So for the fit is I pretty much essentially can get it down to that line, but not distinguish between a small A min and a shallow Q, or a larger A min and a steep Q. That both are equally produce the same results for my data. I can give a value of one parameter if I assume the value of the other, which is for those values, when I show the exact numbers is what I was doing. But the technically more exact answer is given a certain value of Q, here's the value of A min that best fits. And that along those lines, all of those fits are equally valid, equally good fits.
What's the logistics and the actual time that it takes to get some of this data?
Well, most of the observations happen over, say, maybe a few hours. I think spacecraft downlink is maybe once a day, once every few days when it talks to Earth. Cassini does have onboard storage, and one can prioritize certain amounts of data. Usually what happens is this update is relatively low priority. It gets down, but it might not get down right away, so it might take a couple days before it shows up. I know when I started working, most of the data was relatively old. I wasn't waiting on anything. It's more we had the data. It's more of a situation of we have the data, we have a grad student. Let's bring them together so that if data gets looked at and the grad student has something to do a dissertation on.
You have a question on
Yeah, the power law part makes sense to me, because like you say, we always use power laws, but is there any good explanation for why there's a maximum and minimum?
Actually, there is, dynamically speaking. The smaller stuff there was actually a paper published about 2 years ago, that what happens is, selectively, the smaller stuff tends to stick to the bigger stuff, which explains why there is a minimum cutoff law, that the smaller stuff tends to glom on to the rings, to the bigger stuff. So if you turn around and take a reflected spectrum of the ring, you can see plenty of evidence of microns and hundreds of micron size ice grains, but just they're all coating the surface of larger stuff. We don't see them when you do an experiment like this. So there's another explanation, a little bit older in the literature, why there's such a steep cutoff at the larger end, but I think it has to do with collisional processes.
I find these wakes fascinating because they, as a condensed matter physicist, they remind me to emergent many particle quasi-excitations, maybe. And in condensed matter, as in plasma physics, I guess, we use those excitations to get a simplification of the description of the dynamics of the complicated many particle problem. Is there anything you can do here in this context? Can you simplify on that coarse-grained scale the dynamics of the many particle problem?
I think it's being considered. Unfortunately, I'm not much of a theorist, so I haven't worked much in the dynamics of what's going on with these. I know some of the problem is that certain other aspects of the rings tend to disrupt these. For instance, if you are near a spot where a moon is in resonance. But I know this is an active area of research of what the effects of these
Which is again similar to condensed matter, because quasi-excitations have lifetime.
So early on, you mentioned that, I think you said that the minimum particle size had implications for the age of the system.
Right.
And I missed, maybe, did you comment on that later?
Not so much as more of a justification for why we're doing it.
So
It's a bit of a problem with the rings is how much mass is in the rings, especially when you have this new behavior of self-gravity wakes, which lets you kind of trap mass without increasing the optical depth of the system. So having a better handle of what's going on, both in the particle sizes and in, how much stuff is in the self-gravity wakes versus how much stuff is free, basically will let you get a total mass of the rings, is one way. There are some other ways that are going to be going on in the next couple of years with Cassini, which the mass of the rings has to do with the lifetime of the system, both because basically the mass helps stabilize things, and because one of our dating methods is to basically accumulate how much micrometeorites in space, and input from outside of Saturn has accumulated in the rings since its formation. Kind of like figuring out how long it's been since you washed your car by how much dust and debris has accumulated on your windshield. So if you have a bigger ring, it's also possibly an older ring for the amount of impurities we see in the rings.